Hi everyone, I'm Kim Hee-Pin Hu from University of Wisconsin-Madison. Today I'm going to talk about the exact and approximate method for proving unrealizability of synthesis problems. This is a dry war with John Cipher, Louis D'Antoni, and Thomas Raft. Firstly, I'm going to introduce what is synthesis problems. In a synthesis problems, the user will provide two inputs, a search space which contains all candidate solutions, and a specifications which describe what the user wants. And the goal of such problem is to fire solutions satisfy their specification from their search space. Especially in a synthesis problem, which is also called SyGus problem, the specification is usually given as a logic formula, which is like this, and the search space is usually described by a grammar. And the goal is to fire function f in the language of the grammar that satisfies the specifications. Here is an example output and SyGus solver may return us. We choose SyGus as our target since SyGus is a quite popular synthesis framework. There are many applications using SyGus. For example, in our previous work, we were using SyGus to invert string encoders, and in other applications, people use SyGus to compute quantified invariants for programs with arrays. Or people use SyGus to compute their constant time circuits, which can defend their FSSA attack. Now we know what is synthesis problems. Then next, I will tell you what does it mean by unrealizability of SyGus problems. Let's consider synthesis problems in which the search space, the specifications, and the search space are destroyed, so there will be no solutions for these problems. Ideally, we hope the solver will tell us why there is no solution. However, for existing solver, they will just time out or fail to solve such problems when there are infinite number of candidate solutions. The reason why proving unrealizability is challenging is that instead of finding an arbitrary solutions, we need to prove that all candidate solutions, infinite number of programs, cannot satisfy their specification. The next question you may have is that yes, some problems are unrealizable and has no solution, but why would one care about proving it? Let me show you why. In our previous work, when we were trying to invert a function, we asked the solver to find us an arbitrary solutions. And this is what the solver gave us, which is large and unreadable, and it is obviously what we know what we expect. So we want to find smaller solutions. To do so, we restrict the search space to program of size less than 1000, and say we found another solutions, and we further restrict the search space to less than 100, and say we found a solution look like this, which is one line and of size 9. To find a smaller solution, we further restrict the search space to a program of size less than 9, and then we go start. Since you can see this problem has no solutions. That's why we want to prove unrealizability. Since if we can prove the unrealizability of these problems, we can show this solution is optimal. Now, you know what does it mean by unrealizability of the SyGus problems. I will show you the main contribution of our paper, how to prove the unrealizability of unrealizable SyGus problem. Let's first look at an example. In this example, we want to compute a function f in which the f returns 5 on input 1 and returns 3x on other inputs, and the search space contains grammars in which we can use one if then else statement. And in this example output, you can see the function f use one if then else statement. The user may want to ask, oh, we found a solution with an if then else statement. Can we find a solution without using an if then else statement? To do so, she will construct a grammar without using if then else statement and replace the grammar to get a new synthesis problems. Actually, this problem has no solution and it is unrealizable. Why? Let me show you why. If we look at this grammar, there is a solutions which can be produced from this grammar, the non-terminal star, if the solution is either in the language of EXPR1 or it is in the language of EXPR2. Let's first look at the EXPR1. You can see that the EXPR1 can produce terms 1, 2x plus 1, 4x plus 1, and which can be summarized as 2 lambda x plus 1, where lambda can be any natural number. So, to decide whether there is a solution in the language of EXPR1, we just need to check if there exists a lambda such that for all possible input x, 2 lambda x plus 1 satisfy the specification. However, this formula is non-linear and it is hard to be decided. So we restrict us on only two input x equal to 1 and x equal to 2, and we only need to check if there is a term satisfy the specification on these two input, which means that we just need to check if there exists some lambda such that 2 lambda 1 plus 1 equal to 5, where 5 is the value of f1, which can be inferred from the specification. And we also need to ask that the 2 lambda 2 plus 1 is equal to 6, which is the value of f2. Actually, this formula is false, since you can see 2 lambda 2 plus 1 is an odd number, while 6 is an even number, which means that we cannot find solutions in the language of EXPR1. Similarly, we can summary all terms. The terms can be produced from EXPR2 as to 3 lambda x, and we also restrict us on input 1 and 2 and check if there is some term satisfy the specification on these two input. And the answer is no, since you can see 3 lambda 1 is divisible by 3, while 5 is not divisible by 3. So we cannot find solution from EXPR2. I show you we cannot find solution from the language of EXPR1 and EXPR2. So we cannot find solutions in START, which can either produce terms in EXPR1 or EXPR2, which means that this problem has no solution and it's unrealizable. In the previous examples, we didn't prove the unrealizability of a SyGus problem psi on all possible input. We only proved the unrealizability on two input x equal to 1 and x equal to 2. So we call such problem SyGus with example problem psi e for an example set 1, 2, where in the problem psi e, the specification is no longer a full logic formula. Instead, the specification will be some input-output example, for example f1 equal to 5 and f2 equal to 6 here. If we can prove that psi e is unrealizable, which means that there's no solution satisfy the specifications over e, which implies there's no solution satisfy the specification for all inputs. This is the definition of unrealizability of SyGus problems. So it's enough to prove that the SyGus over example problem is unrealizable. So in the rest of this talk, we focus on the SyGus with examples problems and show how to prove they are unrealizable. In practice, such example set can be provided by the user or can be generated by a counterexample guide inductive synthesis framework, or it can be simply generated randomly. In our algorithms for proving unrealizability, the goal is to compute the summary of all terms which can be produced from each non-terminal, for example, the 2 lambda x plus 1 from EXPR1 or the 3 lambda x from EXPR2. Since now we are considering the problem with the finite set of example 1, 2, the value of x is a psi value 1, 2. So the summary of terms can be described by valuations of all terms produced by each non-terminal. For example, the 2 lambda x plus 1 now can be described by a set of value 1, 1, 3, 5, 5, 9 with x equal to 1, 2. Similarly, 3 lambda x will be set like this, and the summary of star will be the union of them. The high-level idea of our algorithm is to first constructing from the grammar constructing an equations, and then solve the equations to get the solutions. If we can get the solutions of V star, we just need to check if the 5, 6 belongs to V star, where 5, 6 is the expected output. If the answer is yes, we know that this problem is realizable for all inputs in this example set. Otherwise, this problem is unrealizable. The question is now, how can we construct the equations from the grammar, and how can we solve the equations to get solutions? Let's first look at how to construct the equations for the grammar. We take the non-terminal EXPR1 as examples. Firstly, we substitute all appearance of x with its assignment 1, 2, and then we construct an equations which contains a new variable v EXPR1. At last, we evaluate all algebraic operators. For example, here we evaluate the sum of 1, 2 to 2, 4. Now we get the equations for the non-terminal expr1, and similarly we can construct the equations for the other two non-terminals. After seeing the first step, we will move to the second step, how to solve the equations to get solutions. I will introduce two methods to solve these equations. The first one is a logical approach, in which we're using the constant Hom clauses, and the second one is an iterative approach in which we're using the Newton's method. Let's first look at the logical approach. Solving the equation with Hom clauses, we encode the equation to Hom clause problems. For example, for the equations v star equal to v expr1 union v expr2, we encode it as a Hom clauses for all x belongs to v star if x belongs to expr1 or x belongs to v expr2. And similarly, we can encode the other two equations to Hom clauses. At last, we just need to check whether the expected output phi 6 is in the value of v start by an assertion. The upside of such problem is that it can be solved by off-the-shelf constant Hom clauses solver. However, in general, this problem is undecidable and the solver may time out. Next, let's look at the iterative approach, which provides us a decidable procedure for a decidable fragment of such problems. In the iterative approach, we solve the equations with semilinear sets. So, what are semilinear sets? If you look at the pair value 1, 1, 3, 5, and 5, 9, actually, this set of value can be represented by a set 1, 1 plus lambda 2, 4, where lambda can be any natural numbers, and such set is linear set, where the set can produce terms linearly from some finite number of base terms. And the semilinear set is a finite union of linear sets. So we assume that the domain of these equations are semilinear set, which means that all variables and constants are semilinear sets. And you can observe that in this equation there are only two operators, plus and unions. The previous work of Javier Espasa shows that if an equation contains only union and plus, and the domain of the equations are semilinear sets, the equation can be solved iteratively in no more than n runs with n number of equations. So we can solve these equations and get the solutions. And we can have a solution. The theorem says that a linear integer arithmetic SyGus problems with finite number of examples is decidable, where the linear integer arithmetic, the LIA, contains only union and plus operators. Actually, there is a more popular background theory, the conditional linear integer arithmetic, which is also called CLIA, in which besides the union plus, there can be more operators like the minors, the Boolean operators, and the if-then-else operators, and the value of variables can also be sets of Boolean vectors. And in our paper, we show that how to deal with these nil operators. For example, for minors, what we do is we push the negation to leaves to remove all minors operators. And for Boolean operators, what we do is we solve the problem in stage. We first solve the integer parts and use the integer solution to solve the Boolean parts and remove the if-then-else operators. And we repeat this procedure until there is nothing change and we reach the fixed point. At last, we can conclude a theorem says that the CLIA SyGus problems with finite set of example is also decidable. More detail can be found in our papers. Then, I'm going to show you our two-NAE and the evaluation of NAE. We built a two-NAE which contains a component of traditional counterexample guide inductive synthesis framework, which can compute a solution if there exists one, and it contains another component which can prove the unrealizability using the equation solvings, which I introduced before, to prove the unrealizable. And in our previous work, we have another tool named NOPE, which can also prove the unrealizability of SyGus problems. So we take the 132 benchmark from NOPE and compare our two NAPE against NOPE. In the evaluation, we have three tools: NOPE, NAPE with semi-linear set, and NAPE with home closest. And the result shows that there are 62 benchmark, the hard benchmark, no one can solve it. And there are 54 benchmark, easy benchmark, all of the three software can solve them. And there are 11 benchmark, only NAPE with semi-linear set can solve. And NOPE cannot solve this 11 benchmark. And there are 5 benchmark, both NAPE with home closest and NOPE can solve, but NAPE with semi-linear set cannot solve. On this 5 benchmark, our tool is 19 faster than NOPE. As a conclusion, we introduce a method to prove unrealizability. For the open problems, we are also interested in, can we find more decidable fragments of SyGus problems? Can we adapt our method to other synthetic problems beyond SyGus? Can we compute the exact complexity of our methods? And that's my talk for today. Thank you for listening. And any question?